All organic compounds consist of carbon and hydrogen. They may also contain oxygen and nitrogen. Other elements may also be present, like phosphorus, halogens, and/or metals, and there's also others, but I haven't listed them. Most compounds, however, are composed of carbon chains bonded with hydrogen. Here's an example of a carbon chain. It consists of, 1, 2, 3, 4, 5 carbons in a row, each bonded with hydrogen. A carbon-hydrogen chain is an organic compound. Here's another one. This one contains oxygen. Carbon can make 4 bonds. Hydrogen can only make 1. Oxygen can make 2. Nitrogen can make 3. Sulfur can make 2. And the halogens I mean fluorine, chlorine, bromine, and iodine, make only 1 bond. Notice that carbon makes the most bonds of all. Here's an example of carbon making 4 bonds, hydrogen 1 bond, oxygen 2, nitrogen 3, sulfur 2, and of course chlorine 1. Carbon can make single, double, or triple bonds. Hydrogen can only make single bonds, as I just said. Oxygen can make single or double bonds. Here's an example of that. Notice the hydrogen makes 1 bond. Double bonded oxygen to carbon, there's 2 bonds for the oxygen, and of course 2 for the carbon. And then nitrogen bonded to carbon, both make 3 bonds. Here are other examples of the same thing. Actually, I'm just showing here oxygen being bonded in a double bond, and of course then single bonds, the CO-C bonding. Nitrogen can make single, double, or triple bonds. Sulfur can make single or double bonds, and the halogens make only single bonds. I'm emphasizing these points because they help you to make the proper structural formulas for organic compounds. And of course here are examples of nitrogen making 3 bonds, 3 single bonds that is, or a double bond with carbon, or a triple bond with carbon. And here is sulfur making single bonds with carbon, then a double bond with carbon, and lastly, of course, a representative halogen, the bromine, making a single bond. Naming organic compounds. Organic compounds are named based on the length of the main chain. A 1-carbon chain, which I guess is not really a chain, would be identified by the prefix meth. 2 carbons eth, 3 carbons prop, 4 carbons but, all the way down to 10 carbons, which of course would be dec. Aliphatic hydrocarbons fall into 3 major categories. Aliphatics mean chained hydrocarbons. Alkanes have all single bonds. The name for any alkane ends in ane. For example, methane, ethane, propane, etc. Those straight chain carbons that have double bonds are referred to as alkenes. Alkenes end in ene. For example, propene, butene, octene, etc. Alkynes contain triple bonds. They end in yne. For example, you couldn't have methine, for example, because it only has 1 carbon, but you could have ethine, which of course would have a triple bond between the 2 carbons in the chain. You could have propyne, butine, etc. Naming hydrocarbons start with selecting the longest chain, even if it goes around the corner. Here's an example of a hydrocarbon chain. Notice the longest chain goes around the corner and consists of 7 carbons. The straight chain consists of only 5 carbons. The name, therefore, would be based on the 7-carbon chain. it would then start with hep, which means 7 carbons. Here's how we name the side chain. Here's our original compound. The side chain is a 1-carbon chain. Notice it's on the 1, 2, 3, 4, 5, 5th carbon from the long end and 3rd carbon from the short end. There's the side chain. Other common side chains could be, well, you could have propyl, which would be a 3-carbon chain, butyl, which would be a 4-carbon chain, ethyl, which would be a 2-carbon chain, etc. Since we have a 1-carbon side chain, this is going to be called methylheptane. There's the side chain again. It's the CH3 or methyl group, thus methylheptane. But we're not telling you where that side chain is attached. It's on the 3rd carbon. Therefore, this would be 3-methylheptane. Now here we have our compound again, and we're going to count from the short end of the chain. That's very important. Before I mentioned that the side chain was attached to the 5th carbon from the long end and the 3rd carbon from the short end. When we identify the name for the compound, we always count from the short end of the chain. Therefore, this would be 3-methylheptane because it is attached to the 3rd carbon. Supposing we had 2 side chains. There's one, it's a methyl group. There's the second, it too is a methyl group. Both are attached to our 7-carbon chain. The name for this would be 2,5-dimethylheptane. Alkenes, as I said before, contain double bonds. Here's an example. Notice that this is a 1, 2, 3, 4, 5, 6-carbon chain, and it has a double bond. Therefore, the chain consisting of 6 carbons will be identified with the term hex. ENE on the end means that it contains a double bond. The double bond must be identified in terms of location. How do we name alkenes with 2 side groups? Firstly, here is our alkene with 2 side groups attached. Notice one is attached to the 2nd carbon, the other one is attached to the 5th carbon. The double bond lies between the 1st and 2nd carbon. Therefore, the name for this alkene would be 2,5-dimethyl, referring to the location and identity of the 2 side chain groups, 1-heptene. The double bond is after the 1st carbon. Alkynes, they have triple bonds. Here's an example of a triple bonded aliphatic hydrocarbon. Here is the longest chain. This time the longest chain does not go around the corner, and it consists of 8 carbons. Therefore, our basic identity will be oct. Here's the side chain. The side chain is attached to the 4th carbon. And notice that it is a 2-carbon side chain, therefore ethyl. The triple bond from the shortest end of the chain is after the 1st carbon. General formulas. Propane. Propane is identified by its ending as an alkane, and all alkanes have the generalized formula CnH2n plus 2, which would give us a formula for propane as C3H8. N stands for the number of carbons, and of course then the number of hydrogens is related to that by the 2n plus 2. propene, which is an alkene, has a double bond, its general formula would be CnH2n. Notice that we wind up then with a formula for propene as C3H6. The double bond requires that two carbons not be attached, so to speak, and therefore its formula differs by two hydrogens as compared to propane. Propyne would have the general formula, as would all alkynes, CnH2n minus 2, and then now again we have two more hydrogens missing to accommodate the triple bond. Common organic groups. Here's one, an OH group, which is identified as a hydroxyl group. Amine. Amines contain nitrogen, and really what it is an ammonia where one of the hydrogens is replaced by a carbon chain. But the group itself is identified as NH2 and amine. Here is an ester linkage. An ester linkage means that it attaches or connects two carbon chains with this C double bond O group. Here are some others. This is referred to as a carboxyl group. A carboxyl group is characteristic of organic acids. Here's a carbonyl group. A carbon with a double bonded oxygen in the middle of a chain is referred to as a carbonyl group. This is an ether linkage. Ether linkage means an oxygen bridge which connects two carbon chains. An amide. An amide consists of a carbonyl group and an amine group combined. Many functional groups are combinations of smaller functional groups, just like I identified the amide a moment ago. Here's another example. A carbonyl and an ester linkage together, an ether linkage I should say, a hydroxyl group and a carbonyl group combined yield a carboxyl group, which is our acid group. An amine plus a carbonyl would give us an amide, just like I mentioned before. Compounds containing functional groups have specific names and, of course, specific reactivities. Carbon chains containing an OH group or hydroxyl group end in OL and are referred to as alcohol. Here's an example of a simple alcohol, ethanol. Why eth? Well, it has two carbons. The ethyl group is C2H5, and if I represent the carbon chain with R, put an OH on the end, this represents a typical alcohol. The name for this would be, well, it could be called ethyl alcohol, or ethanol, which is the term I just used to describe it. Notice it ends in OL. This is the more systematic name. The common name is grain alcohol. Here's another one. A ketone. Any compound that contains this carbonyl group in the chain is referred to as a ketone. Their name ends in ONE, own. Here's an example. We have a methyl group and an ethyl group connected with the carbonyl, the C double bond O group. Therefore, this would be a ketone. And I show that one R group and the second R group are connected via this carbonyl group. This could be referred to as methyl ethyl ketone. Why? Well, a methyl group and an ethyl group are connected by the C double bond O oxygen group. Butanone is the more systematic name. Why? Well, we have 1, 2, 3, 4 carbons. There's the bute, and ONE indicates, of course, that it is a ketone. 2 propanone would be incorrect, since counting from either end of the chain would put the carbonyl group on the second chain, or the second carbon of the chain. Aldehydes have a group at the end of the chain consisting of C double bond O and an H. They all end, the systematic name that is, ends in Al. Here's an example of a simple aldehyde. This could be called ethylaldehyde. Why? Well, 2 carbons again would be ethyl and an aldehyde. Again, this is the older method of naming the compound. A more systematic and modern terminology would be ethanal. Why? 2 carbons ending with a aldehyde group. The Al indicates that. Ethanal would be the more systematic name. Common name would be acetaldehyde. Acids contain the carboxyl group. They end in OIC, oic. Here's an example, a 2-carbon acid. How do I know it's an acid? It has that carboxyl group on it. Here is the general formula for an acid group on a chain, or in other words, an organic acid. And you might guess already, the systematic name would be ethanoic acid. The more common name, of course, is acetic acid. Or there's ethanoic acid, as I suggested, and this is the formula and name for vinegar. Isomers. Isomers are compounds that have the same formula but a different arrangement of atoms. That is structural isomers. There are other kinds of isomers which we will talk about in a few minutes. Here's an example. Butane would have the formula C4H10. It's a straight chain. We know about this already. All single bonds, therefore butane. However, the formula for methylpropane is exactly the same. Here's another example. Propanone and propanal. Both have a carbonyl group. Here are some more isomers. You could, if you look carefully, see that each one has the same formula but a different setup, and therefore it is a different kind of compound, a different setup or arrangement of atoms. Chiral carbon atoms are atoms that have the same atoms attached to them, but they are mirror images of each other. Compounds that are mirror images of each other are often referred to as enantiomorphs. The word chiral refers to being handed. Here's what we mean. Your right and your left hand look exactly the same with respect to the number of fingers, thumb. The difference, of course, is the orientation. It's impossible to superimpose your left hand on your right hand. See, the molecules cannot be superimposed, and here's what I mean by that. You'll notice that on the left side, the purple atom is out of the screen. And if I were to superimpose it by rotating it, that means that the purple atom then would be into the screen. And although at first glance it looks like they could be superimposed or aligned, they really can't be. Here are some other examples of mirror image molecules, so to speak, or enantiomorphs. They are also referred to as optical isomers. Stereoisomers kind of says the same thing. Here's another type of isomer. They're referred to as cis-trans isomers. They involve molecules that have double bonds. The one on the left is referred to as a cis isomer. The word kind of reminds you of the term scissors, and you'll notice that the two atoms on the bottom of the double bond, which I have a block around, a whole other group of organic compounds are referred to as aromatics. Aromatic compounds contain a benzene ring as part of their structure. The formula for the benzene is C6H6. This is its arrangement. I show two diagrams for its arrangement so it's clear. Here is another picture of the benzene ring, and what it shows is electron delocalization. What we mean by this is that the electrons that form the bonds on the carbon atoms more or less spread out over the entire ring. Delocalization means that they kind of move back and forth in these bonds that create the ringed benzene. This is referred to as a resonance structure. Resonance meaning that the double bond and the single bond constantly flip back and forth between the carbon atoms in the ring. So at one instant of time, the benzene ring may look like the diagram on the left, and the next instant looks like the diagram on the right where the double bonds have changed position, and then the next instant on the left and the next instant on the right. Here are some representations of a benzene ring, diagrammatic, so that when you look for a formula that's written, you may see any one of these symbols representing the benzene ring. Some common aromatic compounds. How are they formed? Well, we attach side groups, so to speak, to the benzene ring. In the case of toluene, we have attached a methyl group. And this, of course, could be called methylbenzene, but the common name is toluene. Benzaldehyde has an aldehyde group attached to the benzene ring. Phenol, that means that it's really an alcohol, but it's an alcohol that contains a benzene ring. You can see that because the OH, or the hydroxyl group, is attached to the ring. Here's naphthalene. Naphthalene is two benzene rings together. And then here is a more common substance that you're, I'm sure, familiar with, aspirin. It too contains a benzene ring, as you can see here, and of course other side chains. Cyclics and aromatics can easily be confused. This is cyclohexane. Cyclohexane means that the 6 carbons that compose it are arranged in a ring, but they don't have alternating double and triple bonds. And of course the formula is different because the bond that is not, that is the double bond that is not accommodated, has a hydrogen attached instead. So cyclohexane has twice as many hydrogens as benzene does. But at first glance they look similar because they're both a ring structure. Cyclohexane contains no double bonds, but it does contain 12 hydrogens. On the right we see benzene, which is also a ring structure, but contains the double bonds that we just spoke about, and only 6 hydrogens. So cyclics and aromatics at first glance appear to be the same, but of course are different.